Welcome to week 10 live session of molecular spectroscopy of physical chemist perspective. I am Arkuprabha Chaudhuri. I am a PMRF at the Department of Chemistry, IIT Bombay. I am being a teaching assistant in this course for this semester. Professor Aninda Datta is teaching this course. Currently, lectures week 11 is going on. 11 or 12 is live. Today actually in the last live session or live discussion session, what we have done, that we have discussed the how what are the symmetry, what is the application of symmetry in determining the normal modes of vibrations, and what are actually normal modes of vibration we have discussed, and we have stopped at the determination of normal modes of vibration in D3H point group, example of which is BF3 and CO3, E2 minus carbonate ion. And what we have found out is from the character table and all, what we have done, actually the main thing was that when the atoms are unmoved, those atoms which are unmoved during symmetry operation, actually they are going to participate, actually they will contribute to your character of that particular symmetry operation. And from there, actually what you can do, actually you can determine the gamma reducible representation of that total of all the vibrational modes, and using simple formula of this, AI is equal to 1 over H multiply by a sum over R, or the symmetry operation, chi of the character of the reducible representation of the symmetry operation R multiplied by the character from a irreducible representation of that same symmetry operation. Using that, what we have derived is that gamma vibration, or this reducible representation of normal modes of vibration, consist actually 6 modes. We can also mathematically derive like 3n minus 6, right? 3n is total degree of freedom. Then from that we have deducted the modes of translational motion and modes of rotational motions in a nonlinear molecule. That's why 3n minus 6. And from there also we have got the 6 modes of vibrations are possible. And these 6 modes of vibration actually belongs to A1 dash, 2E dash, there are 2E dash and A2 double dash. Now actually what we are going to discuss is the material for lecture from lecture 44 actually. So I will just change my color here. So internal motion, IR activity. Okay. So here IR and Raman both. So we'll start from BF3 itself. T3H is the, so D3H point group, right? I'll just copy paste the character table from the previous slide, and I will just make it a little small so that okay, I hope you can see what is written. So in this D3H point group, this is the character table. As you can see, there are total number of operations are operation or order of the group is 1 plus 2, 3 plus 3 6 7 9 and 12. That is your H. Okay. And now, and what are the symmetry elements are there? Obviously identity is there, 2C3 operation, rotational axis. Then perpendicular to that there are 3C2. Then there is a molecular plane. Then there is a 2S3 operation is also possible, and there are 3 vertical planes are also there. And now mirror planes. Now what I today we are start with that. So how does this symmetry, so what we have already known that your gamma V is actually consist of your obviously A1 dash plus 2E dash plus A2 double dash. Okay. Now, and we know there are total 6 number of normal vibrations are possible. Right. Now what each of these symmetry, each of these are each of these modes belong to which symmetry species or which irreducible representation. So what can be the possibility that there could be a stretching or bending, stretching, or you can say a compression along bond lengths, right? Suppose this, let me name as L1, L2, L3. What else? L1 and L2, suppose I am writing theta 1. I can use another pen maybe. Theta 1, theta 2, then this I have already. So this is theta 3. Okay. Now, according to this, there could be symmetric stretching or compression, asymmetric stretching or compression. There could be bending, in plane bending, right? What else is possible? Another thing is possible, that is doming. Doming means out of plane vibration. That is, suppose this is going below the plane, that is why minus, and this will come above the plane. But remember, the point group is not going to change. Okay. Or we can also so this can go below, right? So this is just a opposite operation of this. So they are actually same, not same but opposite. Suppose this you can mention as suppose xi, so then it is xi minus, right? Or minus xi. Okay. But that let me write that point group is not changed in the molecular vibration because we are means the because we are still working under the assumption of simple harmonic oscillator. That means the change from the equilibrium is very less, right? That's why simple harmonic oscillator. Okay, so that's why the point group won't change, so we will work with this point group only. So it's not like that your D3H will become something else. So it may think like if there was a sigma H molecular plane, now there is B is going below and the fluorine atoms are going up, then how there is a molecular plane? Or because the change is not much. Okay, just wait for a bit. Now we will see that what is the change in this bond lengths are going to happen with this character table. So I'll just write it here, D3H. That E is there, 2C3, 3C2 dash, sigma H XY, 2S3 and 3 sigma B. Okay, now see with this the L1, L2, L3 will change differently, right? If they change to same extent, then that is a symmetrical stretching. If they compress same, then that is a symmetric compression, right? If so, like that, they all L1, L2, L3, they are all different bases. Okay, and based on that, I will try to get L1, L2, L3, the reducible representation for this category. So what will be that? So upon identity operation, there won't be any change. So the character will be 3 of that transformational matrix, right? Then what about 2C3? So now see L1 will become C3 along, suppose we are performing a clockwise rotation, then L1 will become L3, right? And L3 will become L2 and L2 will become L1. So all the positions are going to change, and as we have already known that if the bases are going to change their place, then they are not going to who, who contribute to the characters, right? So the character will be 0, right, for C3. What about C2 dash? See, during each C2 dash operation, your B and F along that bond is going to be same. So L1, suppose we are now considering only L1, the C2 dash is going through the BF containing L1 bond. Now you will see that L1 is not going to change, right? But L2 and L3 are going to interchange their position. So it will be 1, right? For each C2, the character will be 1. What about sigma H XY? All the 3 L1, L2, L3 are going to be the same, so they will all contribute. What about 2S3? So firstly, obviously there will be C3, they will change their place, and then they will remain the same, but they have already changed their place, so your S3 is also going to be 0. What about sigma V? Again in sigma V along L1, suppose that plane, your L1 is going to fix and L2 and L3 are going to interchange, so it will again character will be 1. Okay, so your L1, L2, L3, the bond lengths or the bonds are actually making a reducible representation like this. Okay, what they are belongs to, if you want to get it, you remember the formula. I hope that AI is 1 over H R chi of the reducible representation character of that, and from character from the irreducible representation. If you operate this, you are going to see your gamma L1, L2, L3 are actually nothing but A1 dash plus A dash. See, it is 3 0 1 3 0 1. Okay, what about now? So this is done. What about the bond angles? So now it is theta 1, theta 2, theta 3. So let's see. So when during identity it will be 3, right, no change. Then again when we will use the rotational axis, then all the thetas are going to interchange, right? So it will be 0. What about C2 dash? During C2 dash, see the theta 2 is going, so suppose I am considering only theta 2 and it is passing through this bond, this BF, this bond. Now this C2, actually theta 2 is going to be same, but theta 1 and theta 3 are going to interchange their place, so only theta 2 is going to, but see the angle, there is no change in that which angle, so angle is going to be fixed. It is not like it is minus theta 2, theta 2 is going to be same, so theta 2 is going to contribute only to that particular character. What about sigma h? All of them are going to be same for S3 also, and if you consider molecular plane, then also you it is character is going to be same, and due to that you are going to get L1, L2, sorry, theta 1, theta 2, theta 3. Going to be A1 dash plus E dash. Okay. Now if you do that, and what about, what else is remain? The doming motion, these are called doming, in plane or out of plane bending, right? So I'll just, but see here all the atoms, so the doming motion will be not like only one F is coming, others are not coming, then it won't be happen, right? Because then the here center of mass is going to change, but in a normal modes of vibration your center of mass is going to be fixed, right? Else it will be a translational motion. So all the doming, so all this movement is actually considered as only one, right? So if your all the things, means what I am trying to say, this doming is, it's not, it's going to put as a character as 1, not as 3 or 4, right? So because these are all happening simultaneously, all at a time, so obviously your identity is going to be, the character will be 3 because no change will be there. What about 2C3? Let us see. So if I change the place, if I rotate it, so the plus are going to be plus, right? So there will be no change in the sign, no change in the movement, right? It will again coming upwards. It will not happen that it is becoming minus. So okay, I have made one mistake. This will not be a 3 because this is 1, because they are all of them actually doing that at a time, means all together that is one motion. Okay, now this is also 1 because there is no change. in the movement. What about C2? If you do C2, then see what will happen. As I think you remember Datta sir's video where he has shown with the panes. Actually, here he took 3 panes and shown that if you perform a C2 axis of rotation along one of the BF bonds, then your suppose I will use this red color here. Suppose you are going, this is your C2L. If you do this, then this F will go here and this F will come here, but now your these F's are actually, fluorines are actually coming out of the plane, but after doing that C2 axis of rotation, it will go below the plane because it will look something like this, the below one, right? So actually they contribute negative, so actually it will be -1. What about sigma h, the molecular plane? Again, during molecular plane, all the movements are going to be reversed, so it will be -1. What about S3? So they will move, but then along sigma h, there will be a reflective plane. So during C3, there is no change. But when you are, the second option is there, that is reflection along the sigma h, it will be the motion will be reversed, so it will be -1 again. What about sigma v? So along sigma v there won't be any change, so it will be 1. So which which symmetry species this gamma domain actually belongs to? If you see 1 1 -1 -1 1, that is 1 1 1 1 -1 -1 -1 1, that is your A2 dash. See, so your the doming motion actually is going to be have the symmetry species A2 double dash, your theta 1 theta 2 theta 3 that have A1 dash plus E dash, but your concern will come because they are actually going to tell that there are 2 A1 dash, but you have already worked out that there is only one A dash. Why is so? So there means we are considering something extra, right? So what restriction we need to put it here? You remember we are taking the angles as theta 1 theta 2 theta 3. Now in the bond lengths there is no restriction, like your this L1 can be this, L2 can be this, and your L3 have to be something else, right? That can be possible, right? Obviously if L1 L2 L3 don't stretch or compress same, then that will not be a symmetric stretch, but it could be some asymmetric motion also, right? But if you but this is fixed that your theta 1 plus theta 2 plus theta 3 have to be 360-degree, it can't be more than that. So if your theta 1 and theta 2 who increase to same extent, then your theta 3 have to be decreased twice that of extent, right? Means your theta 1 theta 2 theta 3 cannot increase altogether. So this is the restriction, that your symmetric bending is not possible. Okay, so due to that, this A dash we can happily deduct. Okay, so as you can see, your theta 1 theta 2 theta 3, these bending motions are actually be part of this E dash, whereas your bond lengths are actually along symmetric stretching or asymmetric stretching, these are actually going to form A1 dash plus E dash, and your doming motion is A2 dash. That's how you see that individual motions. I can't draw them here, that is actually very hard. I don't remember actually that how they are looked like, but if you look at the videos, Sarah has shown the examples of those motions, how they actually obviously you can draw symmetric stretch and asymmetric stretch and all, but I don't remember the exact bending and other things. I prefer that you should go and watch the video, or obviously you can look at the textbook for that purpose, to see that what those bendings actually, those normal modes of vibration actually looks like. But now we have understood these normal modes of vibration, or these kind of vibrations or these kind of motions actually belongs to which kind of symmetry species that we have already obtained in the when we have deconvolute the reducible representation. Now the next part comes that, so these are all till now we have mainly discussed about the vibrational these things. Now we will discuss about the what is actually going to happen with the uh, means now we are going to see that how does it affect the spectroscopic part, right? So as we are discussing vibrational spectroscopy, obviously we are talking about IR spectra, right? What else could be there? Obviously vibrational Raman, right? So what is the effect of this on IR activity or so IR and Raman activity? Okay, so same we will go with BF3. B3H, H is 6, and we already know that comma V with A1 dash plus 2E dash plus A2 double dash, right? And let me also copy the character table, it will be helpful. So now for IR spectroscopy or transition moment integral, if you remember, consist of your, we are talking about vibrational, right? V dash, right? For V, some V, then your dipole moment and your starting one, or let us, obviously all the molecules are there in the V equals to 0, right? So we have to see what is this integral is. If this integral is non-zero, then only it will be IR active, right? What about, so first we will discuss about IR activity. If non-zero, then IR active. We already know to how to look at that transition moment integral or this integrand, right? What is this integrand or square triple product? That is psi v mu psi naught. So integrand have to be symmetric. So we are discussing that if to be IR active, your transition moment integral has to be non-zero, and for that your integrand have to be symmetric with respect to obviously your inversion. Because suppose what I am trying to say, let's suppose there are two states. We'll just briefly discuss this. So there are two states. So we are now considering about this transition, upward transition. So upward transition, this is psi 1, psi 2. So what I am trying to say is your integrand, like psi 2 mu psi 1 should be equal to that of the opposite transition, right? It should not change, the magnitude should not change due to the inversion, right? So your integrand has to be symmetric, that's what I'm trying to say. If this was not the case and your integrand I is actually minus I, which is antisymmetric, then actually your I is 0, right? So that means your TMI is 0, your transition moment integral would be 0. So only one condition, that is antisymmetric condition, that time your transition moment integral will be 0, but other than that, if it is symmetric, then your integral will have, if it integrand is symmetric, then you have a non-zero transition moment integral, right? Now how to get the symmetry right? So if you remember psi v is equal to 0, actually I'm not going to be much specific, but if you remember the I don't remember the normalization constant, I'll write this, and there was some e to the power minus x square. I will write k minus k x square because I don't remember the exact term, some exponential function like gamma function, and there was some Hermite polynomial was there, right? Psi hn, but for this purpose it was h0, something like this, right? So for this, and so let me, not for this but for a common case, right? So psi 0, actually this part was symmetric, and h and psi for psi 0, h of psi is was actually 1. What about, and vibration only takes place delta v equals to plus minus 1, right? That is the selection rule. What about psi 1? Psi 1, h1 psi was actually c psi. So actually symmetry of psi v or psi 1, actually v equals to 1 or v equals to 0. So this is symmetric. This symmetry of this depends on psi, okay? And what about mu? Mu could be mu x, mu y, mu z, and you remove these, all are actually antisymmetric, okay? So symmetric, antisymmetric, it is antisymmetric, then your psi have to be antisymmetric for, means your psi v or the wave function of the excited state have to be antisymmetric for these particular conditions, and then it will be IR active. Actually from here, actually what we are actually coming is that if your normal modes of vibration, if normal modes of vibration contain, if of normal vibration contain actually with one of the xyz, then that normal mode of vibration will be IR active. So for this particular case, see what is happening, that your E dash, so your A1 dash, 2E dash, A2 dash. So we have already mentioned here that your bond stretching was they connect A1 dash plus E dash, your angle or bending in plane, that belongs to E dash. What about your doming motion? Doming motion is actually A2 double dash. So your, if you see your the stretching A1 dash don't carry X, okay, but your XY, they both together actually are there in the E dash. So this is going to be, even if A1 dash is not, as E dash is there, this stretching is actually going to be IR active. What about E dash? Obviously E dash is IR active. What about A2 dash? A2 dash is actually IR active. What about what? So what is the particularity about XYZ? So actually your E dash is actually polarized, XY polarized. E dash XY polarized. What about only Z polarized light will be, that transition will be allowed, Z polarized. Okay. So what about Raman activity? You remember that in Raman case the TMI will be something different. It was final, here it was something alpha delta 2, the quadruple moments kind of thing. So now instead of XY, so I will write if symmetry species CIA of normal mode of matches with the components of quadruple moments quadratic terms, x square, y square, z square, this, then they will be IR active. Okay. So for this particular case, let us see what is happening, that your, what about A1 dash E dash? I will use another color, maybe not black, green. So A1 is actually, this is actually a Raman active, as it has x square plus z square this term. What about E dash? E dash is also Raman active. As you can see, there is quadratic term x square minus y square. So these are also Raman active. What about A2 dash? A2 dash is only IR active, Raman inactive. Okay. Now there comes an interesting situation for, that is known as rule of mutual exclusion principle, or then the rules are not right. Mutual exclusion principle. So mutual exclusion principle says if molecule contains a center of inversion, then your IR active modes will be Raman inactive, and Raman active mode will be IR active. Please wait for a second. Center of inversion, then IR active will be Raman inactive, and vice versa. Okay. So for this, actually, I will go to week 10, that octahedral example we are doing. So I will solve it fast. The penta. So there was a question, right? That pentachloro hexachloroplatinate, right? So I'll just quickly copy this. Not this, only this. Maybe I'll take all of this and this. Here, put them here. I do this. This. You remember this question, right? And they have a octahedral field of symmetry. So octahedral, this hexachloroplatinate is octahedral field, right? So octahedrals are actually, they will have the center of symmetry, right? The center of inversion is there. I will not calculate the whole thing. I will just tell this. If you remember, this was the correct modes of vibration for hexachloroplatinate. I will just draw once. How does this looks like? See, octahedral, Cl, 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 Cl. They were in a plane, okay, and this was the case. Now your for hexachloroplatinate, normal modes of vibration contains your A1G, EG, T2G, 2T1U, T2U. So I am not going into the thing that which vibration belongs to which kind of motion, because there are 1, 2, 3, 4, 5, 6, 7 atoms are there. So there could be multiple, as you can see, how many normal modes of vibration are there. A1G is 1, then EG is 2, 3, 3, 3, 6, 6 plus 6, 12, and 3, 15. Total 15 modes of vibration. 15 normal modes of vibration. But if you see the IR activity and Raman activity thing, this is a centrosymmetric molecule, contains center of inversion, right? So see, your A1G plus 1, it has actually x square plus y square plus z square, quadratic function. So it is actually, I will write it here, it is a Raman active, but there is no xyz term, so IR inactive. Okay. What about EG? EG is, as you can see, this is again IR inactive, but Raman active. What about T2G? T2G is again a Raman active, but IR inactive. What about, then what is that? 2T1U, that is this. If you see, they all transform together, XYZ together. So this is actually a Raman inactive because there are no quadratic terms are there in the basis, right? But they are IR active. What about T2U? T2U, if you see, this is neither Raman active nor uh, neither Raman active nor uh, IR active, neither Raman active. Okay. Okay. So as you can see, so what we have found out here. So see here in a centrosymmetric molecule, the species which are Raman active, so mutual exclusion principle actually playing here, right? So we have proved that with an example, and I urge you to look at other centrosymmetric molecules and other point groups also. Do we have any other point groups here which have a center of symmetry? I don't remember. Let me check our old files. Maybe C2 bit, obviously not. What about, so this is was P3H, TD is not, no, so we have not discussed much center of symmetry, but we can obviously go to um, uh, symmetry Jacobs group, and suppose we want to, octahedral we have already seen. Let us see what about D4H. Does it contain a center of inversion? Yes, it does. So one thing is obviously which have a Z symmetry cannot have U symmetry, right? So similar to this A1G here is, as you can see, it is Raman active but not IR active. What about so for a obviously for a particular molecule you have to see what are the normal modes of vibration, but here what I am trying to say that wherever the quadratic terms are there, there is no xy terms belong to them, because uh, those will have different symmetry, as you can see here also. Where the I is 1 means the symmetric respect to the center of inversion, those are only going to be Raman active. See, where the I is negative, such as this A2U or EU, they have the XY component but not the quadratic terms. But those where I is positive means G, they are only the quadratic terms are there. What about um, does icosahedron have I? No. So you can obviously check various like this and satisfy yourself that we are doing a correct thing. So I hope you are clear with the mutual exclusion principle, and obviously we before going for the, so we have discussed IR and Raman parts, right? So now we will just quickly discuss one thing, that is your electronic spectroscopy, the next part that is coming, right? Very briefly we will discuss. So for electronic spectroscopy, so obviously if you remember the states, then these are your electronic states, E0, E1. They contain vibrational states levels, right? 0, 1, 2, 3, 0 dash, 1 dash, 2 dash, 3 dash, and also there will be rotational lines. These are rotational lines. I will not draw much. I hope this is clear, right? So your actually your overall psi is wave function is psi electronic to psi vibronic. Actually we can do this according to the Born-Oppenheimer approximation. So this tells us that actually your this all we can means actually we can deal them separately. We can separate it out because their motions have different times. So this is actually the basis for Frank-Condon principle. I am coming there. So when a electron is vertically excited, the time scale is very small and nucleus is much heavier than the electron. So at that point of time, the even if the electron is vertically excited, the nucleus doesn't change their position. Okay, so that's why you can separate them out, these wave functions, and obviously your total energy. So this is your total. You can write it terms of E electronic plus E vibronic plus E rotational, and this rotational have uh, energies around 2 to 10 centimeter inverse, where vibronic have 100 to 100 centimeter inverse, whereas electronics deal with 10 to the power 4 centimeter inverse, that kind of order. So they are actually electronics are pretty different, and we can actually neglect the rotational motions for now, and we can work out the transition moment integral with this. It will actually carry your psi electronic psi b dash, right? The final one. It has two dipole moments operator, right? One is electronic, one is the nucleus, and this is psi electronic double dash psi v double dash. This double dash actually denotes the ground state. Okay. Now when a transition takes place, so I will just first write them out. Okay. Now this is, now we can break it down, right? This is only, this operates only on nucleus, so vibrational motion, so I can take these things out. Now if you remember, this wave function is going to be the orthogonal and 0, because they are two different, so they are the two electronic wave functions, right? But this is not going to be 0, not going to be 0, because they are part of two different electronic states, right? So that's why it is not going to be 0, and we are going to get, and if I can write it, the electronic part separate out in the orbital, spatial, and the spin part. Spatial and I can write L, the orbital. So this actually known as your Frank Condon's principle. Integral. It actually, it is something like this. So this is your fast electronic states, and this is your second electronic state. So this is your energy scale, and this is your equals to 0 to 1 to equals to 0, 1, 2. So the vertical transition is given by this Bank-Condon principle, and the overlap of this actually gives you that. So the better the overlap between the vibrational states, better the integral, higher the integral, higher the intensity. So it actually play with the intensity, but this there is this orbital part that gives rise to orbital selection rule, and this spin selection rule. And you have already known that your delta S should be 0, and obviously another delta M is the spin angular momentum along the z axis, that should be 0. This is your spin selection rule. So if this is follows, then it will be non-zero, and your orbitals also there is different orbital selection rule, one of which is suppose the Laporte rule, which tells us the DD transitions are not possible. But here this is more stringent and selection rule. So one way to avoid this is spin orbital coupling, heavy atom effect and other, and here is vibronic coupling. Coupling with go to relaxation of your orbital selection. So I'll not go much deeper into this because the next day anyway, as sir has Professor Datta has discussed in week 10, there he has started with the rotational fine lines. We will discuss that, but this is actually the basis of the electronic spectroscopy. Okay. Now actually we'll actually solve the week 9 assignment problem. So the first question says for a point group, an incomplete character table is given below with one irreducible representation missing. So we need to find that and write it down. So from the GOT, the great orthogonality theorem, we have come to know that the antisymmetry, that thing that your summation, sorry about that. Okay. So about that, you're from working rules of GOT, actually great orthogonality theorem gives us two things, many of things. We are using two things, that sum of your sum over I chi of E, okay, square of that is actually going to give you order. So that is actually order means total number of operation. Here the H is 6. So see what, suppose I am writing this is my A2 B2 C2. Okay, now what I got, 1 square plus A2 square plus 2 square is 6. Then I have A2 to be plus 1 or minus 1, but I know that the dimensionality is always positive, so I am going to get plus 1. Okay, so my A2 is plus 1. What about B2? So that we will actually use the other principle, that is sum over R your ith character of character of E, or character of symmetry operation R as R ith irreducible representation. If you multiply with a different character of that symmetry operation from a different irreducible representation, you are going to get 0, because they are orthogonal. So we will take that thing into also consideration. So we are so let me write now for this is gamma 2. So from A into gamma 2 we are going to get 1 plus B2 plus C2 is equal to 0. So and gamma 2 into E, from that we are going to get 2 minus B2 plus 0. No, I have missed this. See? So this is one mistake. So you need to consider all the symmetry operations, right? So I'll just go back and erase. One into 1, then 2 into B2, because two symmetry operations belong to this class. And then there is 3C2. What about this now? This is again going to be 2 into 1, then minus 3B2, and then there is 0. So if I have two unknowns, two equations, from here I can see that it should be minus 2. I have made a mistake. Should be 2. Okay. So from here I can see my B2 will be plus 1. Okay. If my B2 is plus 1, then this is 1 plus 2, 3 is equal to 3C2. My C2 will be minus 1. So erase this. I got plus 1, I got minus 1, right? So obviously it will be A, right? A or B. It will be A because A or B, because the dimensionality is 1. Now why it will be A? Because it is symmetric with respect to the principal rotational axis or principal symmetry element, and then it will be A2 because it is antisymmetric with respect to the next symmetry element. So it will be A2. So the correct answer is C. Now let's see the next question. The normal modes of ethylene represented by the figure below is given like this. Now we have to see. So this is an bending, and they all bend together. So this normal mode of vibration. So we have to see which are actually changing or not changing. Depending on that, we will get the symmetry species of this particular normal modes of vibration. So obviously when the identity is there, so there is no change, so it will be plus 1. What about C2? C2 around Z, so that is, this is your C2X, C2Z. This is coming out of the board, so this is in a board. So what I am trying to say, I am coming towards me, and out of the plane of this screen. So that is C2Z. So when it rotates C2 clockwise, so you will see, or anti-clockwise even, so you will see that this motion or this normal mode is going to be the same here. They will change their position, they will interchange their position, but they will be same. So my contribution to the character will be +1. What about C2Y? C2Y is your so this is my actually xy plane, or carrying all this C double bond C, this H, okay, that is my molecular plane sigma H, and I can consider this as my x and this as my y. Y goes in plane with between this. So if you consider C2y, then actually you will see that your um, so if you turn that thing along C2, so you have to you can take your hand and think about that. So now if I change from like this, if I can, this H will come here, so it will something be like um, I will come to C2y later. Let us discuss C2x and others. So if you see the C2x, then you will see that when perform a C2x around this H will come here, but they will, the motion will be same. So it will just fall on this. Okay, so it will also be +1. What about I? So center of inversion is here. Along this, if you see, your motion is going to unchanged. Again, it will be 1. What about sigma xy? So the molecular plane, with molecular plane, there will be no change, right? So it will be again +1. What about xz? Means z is coming out of the plane and x is this. So if you do that, the mirror plane xz will convert this to here, and there will be, if you see, there will be no change. So it will be again be character will be 1. What about yz? Yz, see, this reflects upon this, it will also be 1. And as you understand, this will also be 1. C2y, if it goes here by rotation, the movement is going to be same, it is not going to change. Okay, so it is actually belongs to this, belongs to AG group, and AG is only Raman active. Okay, okay, then let's see. So you didn't have to choose all of this. If you have seen, this is this has a center of inversion, obviously, right? So the one which is Raman active, that will be IR inactive, right? Mutual exclusion principle. So you try to see that what is the what is going to be the character of that particular normal mode of I. So if it is +1 or -1, depending on that, also you can come to the conclusion very easily. Okay, that is one trick I am giving you. You can use only that. You don't have to check for all. Okay, now question number 3. Question number 3 says a part of the character table again of order 4 is again given. So this is actually by looking at this, we know this is C2V, right? So for now, I will write here we have A4, B4, C4 D4. Now again the same principle, that 1 square plus 1 square plus 1 square plus A4 square is 4, the order of the group 4. So A4 is also 1 because dimensionality should be 1. So this is, we got it, and this is 1. Okay. Now the second thing, now we have three unknowns, three equation from the antisymmetry equation, so we will do that. So gamma 1 multiplied by gamma 4 will give us 1 plus B4 plus C4 plus D4 is equal to 0. Then B4 plus C4 plus D4 is minus 1. That is your one equation. What about gamma 2 into gamma 4? To give you 1 minus B4 plus C4 minus D4 is 0. So it is B4 plus C4 minus B4 plus C4 minus D4 is equal to minus 1. That gives you 2. Now again we have gamma 3 into gamma 4. That will lead to 1 minus B4 minus C4 plus D4 is equal to 0. That is your B4 minus C4 plus D4 is minus 1, that is 3. So if you 1 plus 2 equation will give you, see, B4 will cut, C4 will remain, 2C4 will be minus 2. So your C4 is going to be minus 1. If that is the case, if you add 1 plus 3, then what are you going to get? B4 is going to cut, C4 cut, D4 is 2, D4 is also minus 2, D4 is minus 1. If you get that, just put that thing into equation 1. We know B4 we don't know, we have C4 as minus 1, D4 as minus 1 is equal to minus 1, but B4 is plus 1. So by that we got all the things, right? We had three unknowns, so, and three equation. So 1 1, C4 is minus 1, D4 is minus 1. So it is the first option. Now question number 4. Question 4, given below is a specific vibrational mode, obviously BCl3 same as BF3, right, with plus and minus denoting movements of representation of atom above and below the plane of the molecule respectively. The irreducible representation of the vibrational mode and its Raman IR and Raman activity are. So if you remember, this will be same as BF3 what we have discussed so far, which is belongs to D3H, right? So D3H point group is also given. So if you remember, this is doming motion, right? And we have just solved that this actually belongs to A2 double dash symmetry. And if you see, A2 double dash has Z in it, so it is IR active, A2 double dash and IR active, and that too Z polarized. Okay, just look at our previous solve, what we have solved, and you will get your answer. Now question number 5, that bond lengths of homonuclear diatomic molecules can be determined with the help of both. Obviously, this question tells us that homonuclear diatomic molecule. So rotational won't be help, right? And because then your permanent dipole moment is 0. So your homonuclear diatomic molecules, you need rotational Raman spectroscopy and electronic spectroscopy. Why electronic spectroscopy? From electronic spectroscopy, if your instrument resolution is very good, then you are going to get your rotational fine spectra, and from rotational fine spectra you will have an idea of your rotational constant B, and obviously if you get a value of B, then obviously you are going to get your bond length. So two options will be correct: rotational Raman and electronic spectroscopy. What about the normal modes of vibration for POCl3? So we will draw it here. So this is your phosphorus, O, and actually your this is actually a pyramidal structure, and the point group is actually C3b. Okay, so from here first we'll mathematically let us see there are 5 atoms, so and nonlinear, so 3n minus 6, 15 minus 6, 9 will be there, 9 normal modes of vibration. From the first option, this looks correct and this looks correct. These are not 9 modes of vibration, are not there, right? Actually there are. So 3 into 5, 1, 2, 3, 4, 5, 5, 15. So I have made a mistake. These are not, but this is correct. But out of these two, which one? So mathematics don't help us there. So we have to again look at the symmetry. So this is C3b, and if you remember the character table, there was obviously E was there, 2 C3 was there, and 3 sigma V was there, and A1, A2, E was there. First one was totally symmetric, second one was like this, and this was what I remember, 210. Do we have it? Yes, C3b. This is also C3b. So 2 minus 1 0. Okay. So this is for C3b. Point group, the character table. Now let's see for POCl3, what are the total number of unmoved atoms? That is for E, all the 5 will be unmoved. What about C3 operation? Only P and oxygen will remain fixed and other will change. What about sigma V? On the plane, each plane there will be 3 atoms, so those will be unmoved, so it will be like this. What about your gamma XYZB? Better we have C3b point group character table with us. I'll just copy paste it from here. So for this particular question, we don't require the cubic part, so I'll just ignore that. Okay. Now gamma XYZ, XY they transform together and Z is here, so A1 plus E, that will be 3, 0 plus 1, and so your gamma XYZ into N or gamma 3N, total number of modes of vibration will be 15, 0, 3. What about your gamma rotational? What are they belongs to? They have A2 and E symmetry, so 3, 0, minus 1. So actually your gamma v is n into gamma xyz minus gamma xyz minus rotational, translational and rotational, so it will be 9 0 3. Now if you calculate your n of or a of a1, you are going to get your total, your order is 6. Now 9 into 1 1 plus 0 plus 3 into 3 into 1, that is 9, you are going to get 3a1. What about a2? 1 upon 6, 9 plus 0 minus 9, so it will be 0. What about AE? 1 upon 9 into 2, 18 plus 0 plus 0, so 3. So your gamma v is actually 3a1 plus 3e. So actually this is also wrong answer. This is the correct answer. See, from mathematics you can only guess it. If that is the only correct answer, you will be able to solve, but you need to have this symmetry thing keep in mind to get the actual and correct answer. Okay. Okay, now I guess this is the last, no, this is not the last question, we will have something more also. So the pair of symmetry point groups associated with only polar groups. So for polar groups which like polar groups like for water, and if you remember ammonia is a polar group. So to be polar means dipole moment should be there, so it should not have a plane of uh, symmetry. If it is linear, then it should not have a plane of symmetry, right? So okay, like it should not be a carbon monoxide, a carbon dioxide, then it is d sigma h. So actually your answer is C2V and C sigma V, right? Like HCN or carbon monoxide, right? So they don't, they have C sigma C infinity rotational axis, but they don't have the molecular plane. Okay. Now question number 8, for water molecule, the electronic transition from ground state to an excited state of B1 symmetry is, C2B point group is given, and it is said that the electronic transition from ground state to excited state is B1. Then what is the, is it allowed or not? Obviously if you see the B1, it carries X, so it will be an IR act, so it will be allowed, and if it is allowed, then it is actually B1, right, or B2, B1, so it is X polarization, allowed with X polarization, but not allowed with Z polarization or Y polarization, right? So this is the correct answer. So actually as it is already time 10 a.m. 10 p.m. sorry, 10:05. Actually I have started a little late, I was doing one experiment, I am very sorry for that, but we will be stopping our session here. I had a few more questions, but which are fairly easy actually. If you look at this, these are, you just need to multiply it. We'll start it with the next class then. But we had some IR spectroscopy problem which are here. I will keep this thing in the notes for your reference, and you try to solve these things, and we will start from this question maybe on the next week, and then we will go to the rotational fine spectra or week 10 materials what Professor Aninda sir has already discussed. So with that I will finish today's session. I hope it was a useful session for you. With that, let us stop. Thank you for listening.